And so the answer to this is our covariance matrix is sigma x squared times 1, 2, 2, 4, and we found out that this is sigma x squared times a matrix made from our eigenvectors, which need to be normalized, times the diagonal matrix with the two eigenvalues times Vt, and we found out that lambda 1 was 5, lambda 2 was 0. So combining those two, we get 5 sigma x squared and 0 times V and Vt. So in our turned coordinate system, we have a variance of 5 sigma x squared along one axis and 0 along the other axis. And so indeed, this is the square root of 5 sigma x squared, which is the square root of 5 times sigma x. So now let's have a look at the probability density function again. So in the 1D case, we had the following. P of x was 1 divided by square root of 2 pi times sigma times e raised to the power of minus 1/2 times x minus mu squared divided by sigma squared. And I can now just rewrite this as 2 pi sigma squared raised to the power of minus 1/2. So I square the sigma, but then I take the root again. And so it's exactly the same since sigma is non-negative. Times e raised to the power of minus 1/2. I'll just write x minus mu times 1 divided by sigma squared, which is sigma raised to the power of minus 2 times x minus mu. So in the 1D case, that doesn't actually make sense to separate the x minus mu squared into a multiplier before and one multiplier after the sigma raised to the power of minus 2. But then you can see the analogy to n dimensions. Now my sigma will be a matrix. So I'll take 2 pi times sigma, and it contains already the squared elements, so I don't have to square that. And I will have to take the determinant of this raised to the power of minus 1/2 times e raised to the power of minus 1/2 times x minus mu, and now the x and mu are vectors, times the covariance matrix, and it already contains the squared values, so it's raised to the power of minus 1 times x minus mu. And since these are now vectors, again, I need here a transpose to get this quadratic form. So this is the multidimensional Gaussian or normal distribution, where x is an n-dimensional vector and mu is also an n-dimensional vector, and the covariance matrix is a matrix of n rows and n columns. Now after we understood multidimensional distributions, let's have a look at our Kalman filter again. So as you remember, our dynamic Bayes network looked like that. We were in a state x t minus 1, we made a transition to our new state xt using in addition the control ut, and being there, we measured and obtained the measurement ct. And so in the one-dimensional case, we had the following prediction. So we assumed the linear prediction model where the old state is multiplied by a factor and then we added some control. Now conventionally, instead of just taking ut, we will introduce a factor bt which multiplies the control and thereby converts from control space to the state space. So this was our functional equation, and we would have then also to add some noise, which is also called the system noise. And using that formula, we obtain that our predicted state is just the multiplication of our old state by a plus our control, and again the only difference being that we now multiply our control by this additional factor bt. And for the variance we obtain that it is the old variance multiplied by our linear factor, which needs to be squared plus our system noise. And so this was our way to represent our predicted belief using the first and second moment of a Gaussian distribution. And in the second step we had a correction, so we measured a value c, which should be equal to ct times xt plus some noise. Now this is the measurement noise, and we were required to put together our new measurement and our predicted belief to get our new posterior belief. And we did so by defining a Kalman gain. And using that, we computed our new mu, which consisted of the predicted mu plus the Kalman gain times the innovation, which is our measurement minus the predicted measurement. And we also computed our new variance, which was 1 minus Kalman gain times c times the predicted variance. So in those two values were our new belief at xt. Now let us see how this looks like in n dimensions. Now the prediction is exactly the same formula, except that we now use matrices instead of scalar values. And for our predicted mu, we also get a vector, which is computed in exactly the same manner as in the 1D case, with a and b replaced by matrices and mu replaced by a vector. And for the new covariance matrix, we obtain this formula, where the multiplication with a squared is replaced by a left multiplication with a and a right multiplication with at, and the sigma r squared is replaced by the covariance matrix of the transition. And for the correction, we have again exactly the same formulas with a scalar replaced by a matrix and the scalar xt replaced by a vector xt, and we obtain the following Kalman game, which seems to be more complicated as in the 1D case, but if you have a closer look, you see the following. In the numerator, we do have our predicted sigma times c. This is exactly the same as here in the numerator. And in the denominator, we have this term. So the c times sigma times c, that is the c square sigma square, plus the measurement noise covariance matrix is the same as here, plus the measurement variance. So it's the same formula adapted for the n-dimensional case. And then we get our new mu. And surprisingly, this is exactly the same formula, only that mu is now a vector, k is now a matrix, and c is a matrix as well. And for our new covariance, we get the identity matrix minus k times c times the predicted covariance. So as you can see, the formulas for the n-dimensional case, they are generalizations of the one-dimensional case. And although the derivation of those formulas is a bit more complicated, you can clearly see the symmetries between the left and right side. And so again, if you're interested in the derivation of those formulas, this is explained in detail in the book of Thrun, Borgard, and Fox, Probabilistic Robotics. Now assume that our system state, which is a vector, consists of our x position, our y position, and our heading theta, and so this is a 3 times 1 matrix or a column vector. Then assume our control consists of our left and right motor reading. So this will be a 2 times 1 matrix. Now let's just do the following quiz. I want to know the dimension of all the matrices in the formulas. So what is the dimension of A? Is it 2 times 2, 2 times 3, 3 times 2, or 3 times 3?